So this is chemistry, and we really like trends. If you think back in Gen Chem 1, when you were looking at the periodic chart, you would learn things on the chart where like it would go in this direction and increase the electronegativity, and we would say, oh, it goes in this order, except for this one, and then sometimes this one. But we like to put things in these boxes and say, this reaction does this every time. And that's what reaction order is all about, is we are putting reactions that are all very different in little boxes, because once you get something in a box, you can say a lot of things about a certain box. So this is our first box, is if we can get something to fit in a box that is, as we call it, zero order. And I get the 0 because my exponent here is 0. Overall, this reaction has an order of 0, and with respect to C, the reaction has an order of 0. So you can talk about it in terms of just this one or in terms of the whole reaction. You'll see some more examples of this, don't worry. Once we find out that something fits in that box, we also have to kind of tweak it a little. So that's what this thing is about. This is a constant, and this is called the rate law constant, and it is one of those constants that is not like on a chart and stays the same. It's different depending on the reaction and the conditions that you're talking about. So it's unique to each reaction. And this could be a number, like it can be a wide range of numbers, anywhere, like 2 times 10 to the 5th, all the way down to like, 1.5 times 10 to the minus third. Like there's a nice little range of numbers that can be. But what it is we find it for each reaction. We're just like, that's the K constant for that reaction at room temperature. So every rate law is going to have that in it, and it's also going to have some kind of a reactant in brackets raised to some value right up here. So let's look at our next box. Our next box is going to be a first order reaction. And the reason it's first order is because my exponent is a 1. So again, the order of the full reaction, you would actually add all the exponents in the rate law, but there's only one exponent. So this is first order with respect to A. It's also first order overall. Now we have a few options for how something could be second order. So it could just be that the reactant, and there's one reactant, but it's second order. It could also be that we have 2 reactants, and this is why it matters whether we're talking about the overall order or not. But our boxes are talking about the overall order, like second order overall. That's how we're classifying these reactions. But you can also say that this is first with respect to A, or that this is first with respect to B. And finally, this last one is just a crazy scenario to kind of show you a few things about order. We will only be talking about these 3 boxes, and we will actually especially be focusing on this box. There's a lot you can do with this, especially when we get to radiochemistry. But we're only talking about those 3 boxes, and specifically within this box, we're going to be able to come up with some equations, but they will only fit this version of this equation. So we'll repeat that at the time, but I'm letting you know that we aren't talking about these crazy reactions that have all these orders for a lot of reasons, except to have you calculate the overall order. So in this case, the overall order comes from adding up all those exponents. So that gives us that this has an overall order of 8.5, which is a really kind of a crazy order, right? This is 1/2 order with respect to A. It's third order with respect to B, and it's 5th order with respect to C. Note, when you have a fraction as an exponent, and we will not have this happen very much, this actually means that this one slows down the rate. The more of this that you have, the slower the rate is going to become because it's a fractional exponent. It's like saying 1 over that. So that's the other thing to know about the orders. These are great questions to get right on exams because they're very, very quick. And everyone is always trying to categorize reactions by their order when you're in kinetics. So it's a great thing.